You know how they say the third time's a charm? It's a lie. Evil, evil lie. This will be the fourth time that I've tried to make this video, and the darn thing keeps stopping recording. So if this one doesn't work, I'm gonna give up. No, I'm not gonna give up, but I'll figure something else out. Okay, so here we go. Rolle's theorem. Usually we cover Rolle's theorem and mean value theorem in one day, but we're doing half a day and half a day. So this half of a day we're going to spend on Rolle's theorem. We're going to skip mean value theorem. Rolle's theorem in itself isn't all that important in terms of questions being on the AP exam, but it led to the mean value theorem. Without Rolle's theorem, we may not have ever had the mean value theorem, and the mean value theorem is much more significant. So, Mr. Rolle said, let f be a function that satisfies the following three conditions. First, f is continuous on the closed interval from a to b. Second, f is differentiable on the open interval from a to b. And third, the y value at a, f of a, right, has to equal the y value at b. So the y values at the endpoints of the intervals are the same. Those three statements are essentially your if statements of the theorem, and just like any other theorem, you cannot make the then conclusion until you've confirmed the if statements. Once you've confirmed the if statements, Rolle says, then there is a value c, that's an x value, in the interval, so in between a and b, such that f prime of c is equal to 0. The derivative is 0. So, draw, sorry about that, some graphs. So here we go. First time I did this, I had these blank, and I did them with you, essentially, but fourth time's a charm. Anyways, okay, so you'll see that my hand is in the way a little bit. I have a and b, right? That's my interval, and my y value at a is the same as my y value at b. So that's the third condition. The first two say I need to connect those dots with a continuous and differentiable function. Continuous means that the left-hand derivative, let me try again. The left-hand limit is equal to the right-hand limit is equal to the function value at every point on the graph. Differentiable means, again, let me back up. Sorry, this is the fourth time I'm doing this. So if it's continuous, then there are no holes or jumps or asymptotes. Differentiable means that the left-hand derivative is equal to the right-hand derivative, which means there are no corners or cusps. So I have connected these two dots with a continuous differentiable function, and you will see that there is a place where the derivative is 0. Remember, derivative is 0. Derivative is the tangent line. Derivative is the slope of the tangent line. Slope of the tangent line is 0, means that it is horizontal, and you can see that this is that mystical c value, that x value in between a and b, where the slope is 0. Slope of the tangent line. What if I connect the dots in a different way? What if I just connect the dots with a straight horizontal line? It has to be horizontal to connect them if the y values are the same, right? So if I connect them, that is continuous and that is differentiable, then every single value in between here qualifies as that mystical, magical c value, because the derivative at any point on this line is 0. This is a constant function, and the derivative of a constant is 0. Another way of thinking of it is that the tangent line, well, the tangent line to a line is the line itself, has a slope of 0. Okay? And then lastly, I could connect it in a more creative way, and in which case I would have more than one c value again, just like the previous one. So I'm connecting it with a smooth continuous curve, meaning it is continuous and differentiable. And I can see that there's 3 places where the slope of the tangent line is 0, or the derivative is 0, so those 3 would qualify as that magical, mystical c value. So, back here. Below those graphs, that's mean value theorem, that's next time. This is also directly related to mean value theorem, so we're going to skip that for next time. So halfway down page 12, we're going to do an example of Rolle's theorem. So I've got that written out. My arm feels like it's going to fall off from holding the iPad, but this is going to be the one, I have a feeling. So here's our example. The example says to verify that the hypotheses are satisfied. The AP exam's not going to tell you. I see if I can, there we go. The AP exam's not going to tell you to satisfy the hypotheses. You've got to know that yourself. Not only that, but the AP exam's not going to tell you it's a Rolle's theorem or a mean value theorem problem. You've got to recognize that. We're going to do some mean value theorem FRQs, I think later this week, or maybe this is for Thursday, so maybe it's Friday or Monday. I don't really know. Okay. So anyways, first condition, f must be continuous on the closed interval. Well, back in chapter 1, we learned a theorem that said polynomials are continuous everywhere. Think about the graphs of polynomials. They are smooth continuous curves, okay? So when you're working these problems, they're not all going to be polynomials. You've got to be able to envision the graphs and know if those graphs are representing continuous functions. Do they have jumps, asymptotes, holes, okay? So polynomials are continuous everywhere, so of course they're going to be continuous on a closed interval. Polynomials are also differentiable everywhere because polynomials don't have corners or cusps on their graph. So of course they're going to be differentiable on the open interval from 0 to 3. And again, if this function were something other than a polynomial, for example, excuse me, something involving a sine. Well, you know, sine doesn't have corners, cusps, jumps, holes, anything like that. So you can make the conclusion that it is continuous and differentiable because it's a trig function. Oh, excuse me. Okay. Third if statement wants me to find f of a, where a is 0 in this problem. And I plug in a 0. 0 squared minus 3 times 0 plus 2. Also wants me to find f of b, and b is 3 in this problem. The interval, remember, is from a to b. So I plug in a 3 and I get 2, so those are equal. Third condition is satisfied, okay? So then by Rolle's theorem, there's value c. I just literally copied the then statement, except I added the fact that I was using Rolle's theorem. Oftentimes on the AP exam, when you're doing a mean value theorem problem, you need to state the theorem. There are intermediate value theorem problems on the AP exam as well where you have to state the theorem. Rolle's theorem, like I said, probably won't be on the AP exam. But anyways, okay, so there is some place. So I found f prime of x, just taking the derivative of my original function, which is super duper easy, right? They want me to call it f prime of c. Okay, fine, I'll change it to a c. No biggie. And they tell me that f prime of c will be 0 somewhere. That's what Rolle came up with. So if I add 3 and divide by 2, I can get the answer that the place where the derivative is 0 happens at 3 over 2. The c, or the x value, happens at 3 over 2. So this is technically the end of the problem, but I want to confirm it. Okay, and since I don't have a graphing calculator, I'm going to call this the graphical. Remember, we haven't talked about this in a while, but we talked about graphically, algebraically, numerically, and written, right, on calculus. So if I were going to start graphing this, I would probably want to complete the square to get this into vertex form so I could shift it right and down. I didn't feel like graphing it because I felt like that was confirmation enough. But completing the square, remember, take the b, the coefficient of x, divide it by 2 and square it, gives me 9 over 4. I can't just add 9 over 4 though, so I have to undo it. And the whole point of that is because now I can factor that x squared minus 3x plus 9 over 4 is a perfect square. It will factor to x minus 3 over 2 quantity squared. And then 2 minus 9 over 4 is negative 1 over 4. So if you remember anything from your Algebra 2 or pre-calculus, you'll remember that when it's in vertex form, the x minus h plus k. So x minus, the thing after the minus sign is the h, so the x value of the vertex. And then this was a plus k, so that negative 1/4 is the y value of the vertex. Now, why am I talking about the vertex? Well, what kind of graph is this? This is a parabola. So where is there a horizontal tangent, or where is the derivative equal to 0 on a parabola? Ding, 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 it's at the vertex, right? So we've confirmed in one way that the horizontal tangent is at 3 over 2, just like we saw from Rolle's theorem. Algebraically, if you can remember the formula for the x coordinate of the vertex, x equals negative b over 2a, and then going back way up there, your b is negative 3 and your a is 1. Remember, ax squared plus bx plus c. So negative 3 over 2 times the a. 2 times 1 is 3 over 2. So again, I've confirmed that the vertex happens when x equals 3 over 2. And again, I can confirm then that means that the derivative is 0 at that x value, because that's the only place on a parabola where there is a horizontal tangent, or the derivative is equal to 0. Holy moly, I made it. Okay, have a good day.